Hello everyone, my name is Jinghong Lin. I am a PhD student from University of Notre Dame. Today I'm going to present my paper, SENET, a semantic web for supporting automation of software engineering tasks. Natural language interfaces are popular nowadays. People can use them to play music, answer questions, order products, and to perform hundreds of other tasks. Natural language is also emerging in the field of software engineering as means of querying data within specific tool or IDE and to support even more general project-level queries. For example, researchers have proposed a Tiki to support stand-up meeting in agile development, Jarvis for the program comprehension, and other tools even for the code development. But a very general challenge this natural language interface needs to address is connecting the user vocabulary to the project vocabulary. Taking following two queries, for example, user may ask which classes are implemented to prevent the preliminary hazards. In this case, classes refer to the files in the source code. However, project may directly use code to represent this type of artifacts. In second query, user asks about the customer testing, which is actually the acceptance test in the project. So natural language interface can generate inaccurate or misleading results for the users if they cannot match the vocabulary correctly. To address this problem, we propose to build an extensible semantic network for the concepts in SE domain. The concepts in such a network are connected with each other if they are related from a semantic perspective. The basic idea of our method is that we firstly construct the semantic network through data mining, and then we dynamically expand the network with machine learning techniques. We found that the SE glossaries can provide the concept and their relationships in very high quality. Take the following two glossary items for example. The concept address field is considered as synonym of the address part and is contrasted with the operation field. The concept algorithmic language is considered related to various of the concepts, such as algebraic language, Glossary Processing language, logic programming language, ACT. So the workflow of our method is demonstrated as the following figure. We will firstly collect the SC glossary in the SE domain manually, and then extract the terms and their relationships with the regular expression. Then we will argument the relationship we have collected and formulate our initial models as the SENET. And then, with this initial network, we will train the machine learning models to automatically find the relationship between the unseen concepts and the existing ones in the model already. And then in the following two steps, we have evaluated the model accuracy and applied it for the case study, which matching the vocabulary between a user query and the project data. And in the first step, this is the glossary we have collected. So as you can see, the contribution of each glossary varied very differently. So mainly in the first three projects, the first three glossary are contributing the majority of the phrases and the relationships in our concept model. And after argumenting the relationship, the initial concept model will contain around 1,400 related relationships, and 700 hypernyms, and 300 antonyms, and 400 synonyms, and 200 of the acronyms. To train our machine learning models, we need to collect the context for each concept. We find three types of context from different sources. Firstly, we collect the definition of the concepts from the online encyclopedia. Following is an example of the collected concept from the pcmac.com. And secondly, we collect the QA data from the Stack Overflow. We expect to get the conclusions about the concept from this type of context. And then finally, we'll take the column relationship from the general purpose semantic network, such as WordNet. With this context, we then conduct feature engineering to build the features for our machine learning model. Our feature can be categorized into two types: the lexical features and the semantic features. Lexical features analyze how likely the two concepts looks like. We use the added distance, common token numbers, and the shared prefix and postfix to judge the lexical similarity. There are a total of 7 lexical features in our models. And the second feature the semantic features measure the similarity between the context document behind the two concepts. For example, we use a vector space model score to evaluate if the concept having a very similar definition, and if their tokens have very overlapped syntax in the WordNet, and also if their question answering contexts mention each other or not. There are totally 5 semantic features in our model. Then we applied the features to 3 different models, including the space supporting vector model, random forest, and the 3-layer feed-forward neural network. During the training stage, we split the training relationship into 10 buckets and then executed the experiment with tenfold validation. The results show that the random forest have the lowest F1 score, and the FN have higher precision than the SVN, even when they have a very similar F1 score. So in this case, we will prefer the precision to get a more accurate result. Thus, we will choose the FN as our model. We then apply our model to a case study. In this case, we try to map the vocabulary between the user query and the project artifacts. We manually collected 67 SC concepts from 59 user queries, illustrated here, and 96 concepts from the project artifacts. We manually identified 25 mapping between these two sets of the relationships. Then we applied SENET to find the relationship among the two vocabulary we have already extracted. Concepts in SENET are recognized as mapped or matched through 2 ways. Firstly, we will find the path between the user term and the project term, then sort the result by the length of the path. If the true result exists in the top 10 result, then we'll consider it as a successful matching. And the second method is that we leverage the classifier to directly predict the affinity of a user term and all the project term. Then we rank the result by the prediction score. If the true results again exist in the top 10, we'll consider it as a successful matching. Following are a few examples where the SENET can successfully match the user terms and the project terms. By evaluating the result with our manually created golden set, we find that the SENET is capable of mapping 13 out of 25 cases. However, we also find that if we reduce the threshold to 1, then this score, the hitting ratios, will reduce dramatically. This result indicates that our approach is not very robust and need further improvement by adding more data and even more features. So to summary, in this study, we developed a semantic net for SE domain and used it for supporting requirement-related queries. This network was initially built with concepts finding from the SE glossary, and further extended through a feature-based machine learning model. We evaluated the network by finding that it is capable of supporting the vocabulary matching tasks. However, the accuracy actually needs further improvement by adding more data and more features. So thank you for listening and attention. This is my presentation.